Hello everyone. Today is the 62nd day of Leetcode 75 challenge. Let's begin with the 62nd question. Question 790 Domino and Tromino tiling. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given an integer n which represents the width of a 2 cross n board. Okay. You have two types of tiles, 2 cross n domino. 2 cross n domino looks like this. Okay. L septromino. L septromino looks like this. Okay, great. Which is a tile that covers three cells and can be rotated in any directions. Okay, and your task is to complete the cover completely cover the 2 cross n board using any combination of these two piles. So when it says 2 cross n and we will be given an n value, suppose it is given to us as 3. Okay, so it becomes 2 cross 3, right? 2 cross 3 means 2 rows 3 columns. Great. So they're saying us that our task is to completely cover the 2 cross n board using any combination of these two tiles. Okay, every cell in the board must be covered with exactly one tile. Two tilings are considered different if there is at least one pair of adjacent cells that is covered by a single tile in one tiling but not in the other. Basically they're trying to say that if you have this particular thing, right, so you could place it here, this way, this way, this way, right? Or if not this way, you could also go with this way. You're putting here the this one tile, right, this way. So this is the thing they are saying, that you have to completely cover everything. Okay, and return the total number of distinct ways to the tile board, and we have to use modulo of this because the result could be a larger value. So that is why we have to do a modulo of this particular thing. Okay, so I hope you understood the problem explanation. Let's see the constraints is the n value is from 1 to 1000. Okay, so this was all about the problem explanation. So let's move to the next slide. Now let's understand the input output explanation. So if you could see n equals to 3, right, which means that 2 into n was there, so 2 cross 3 it will become. Okay, so we will be having this. Okay, great. So here we know that we have two kinds of tiles. One is this, another one is this, right? Okay, let's put this tile first. Okay, we got one combination here. Let's draw another one. Okay, let's try the another combination. We're taking this one and we're taking the same bar this way. Great. Now let's try taking this one. Okay, this gives me a pattern here. And what else it could be? This also creates a pattern. Okay, then this also creates a pattern. So these are the ways. These are the 5 ways, right? When n is equals to 3. Okay, now let's see another. If n is equals to 1, we have only this, right? So we can only use this block one time. That's all. That's why the output is 1. So I hope you understood the input output explanation here. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. So let's do it by understanding the goal first again. So we are given an integer n representing the width of 2 cross n board. Okay, and we are also allowed to use dominoes 2 cross 1, 2 cross 1, which is this one as we know, and L sep tiles covering 3 squares. Okay, great. The task is to count the number of different ways to fully tile the board using these tiles. Okay, two tilings are considered different if any pair of adjacent cell is covered by the same tile in one configuration but not in the other. For example, what they're trying to say here is that if this is what you have, right, and if you are filling this tile this way, the other tile should not be filled in this way itself, right? This is the gap you are having here, so this is incomplete. So what could be the brute force? Now since they are asking for the maximum number of combinations or all the combinations, Okay, and when the question is of type like you have to find all the combinations, or you have to find the maximum sum of all the combination, minimum sum of all the combinations. When there is a combinations and you have to figure out all the possible, let me write it here, all the possible ways. Just don't think about anything, just come to recursion. That's all. When, because you have to look at each and every path, right? In that scenarios, the recursion is the foremost thing that should come to your mind, and after that you could go to another solution if it is, if any is there. Okay, but the issue with the recursion here is that each tile in every possible position recursively, but it leads to an exponential time complexity, right? The time complexity for this particular brute force is not actually 2 to the power n. I just wrote for the explanation of the exponential part, but the actual time complexity for this is 3 to the power n. Okay, because for each cell we call up to 3 sub problems, and what are these 3 sub problems? I will let you know, but now I cannot, because that is the intuition we have to build up, right? Now let's try to visualize the process. Okay, if 2 cross n is there, right, and if 2 cross 1 is there, we have this as our, you know, board. So here only we can place 1, right? So the output is 1. When uh, n is 2, the board comes out to be of this way, right? Here we can place this way, and again if we place it, we can place it this way, this way. Therefore the output is only 2 here. Okay, when n is 3, we already saw earlier, when n is equals to 3, we have 5 ways. Okay, now when n is 4, let me draw few. Okay, so for 2 into 4, when n is equals to 4, I have drawn 4 examples here. If you can see, this example can be of one more type, right? Plus 1. So this becomes 2, total 2 here. This is 1 here. This is 1 here. This is 1 here. It's 2, right? So it's 2 plus 2, 4, 5, right? And we can see 11 ways are there, because if you can see this one, this pattern can also be drawn as this way, right? If you can see the green color boxes, so this becomes another, it becomes sixth, right? Similarly, if you can take this example, if you thought of making it this way, then this is the another way, right? And here you can place one. So this is a seventh way. So similarly, there could be, if we do the vice versa of this, becomes 1, so it becomes 8. So similarly there are 11 ways, and for 5, when n equals to 5, there are 24 ways. So you can draw the patterns and observe the how many combinations are created. Since I have already drawn it and I have the understanding of it, so I'm just saying that when n equals to 4, I have till here I have given total 8 combinations of 4, but there are 3 more, right? And when n equals to 5, there are 24 ways. So these are the things, right? And please focus on this. This could be our base case. This could be our base case. Okay, now let's try to visualize. Before reading, do not read this part right now. Okay, when n equals to 1, output is 1. When n equals to 2, output is 2. When n equals to 3, output is 5. When n is equals to 4, output is how much? 11. When n is equals to 5, output is how much? 24. Correct? Now if we try to break this particular number, okay, we know that we have been given 2 cross n board. Why? Because if we write 2 here, and if we try to multiply it by n minus 1, or not n minus 1, if we multiply 2 with 11, then we add 2 here, how much does it gives? It gives us 24. Correct? Similarly here also, if you try to multiply 2 into um, 5 plus 1, it gives us how much? 11, right? And here if we try to multiply it by 2 plus 1, we get 5. Also let's take the case for n equals to 0 also, so it will be of course 0. And here if you try, and okay, now let's stop here. Okay, let's stop here. Now focus on these three. This will be our base case. Why? Because if n is equals to 0, it is 0. If n is equals to 1, there is no more combinations. If n is equals to 2, there are only two combinations, right? But when the value of n becomes 3, we have a lot of combinations right now. And if you can observe here, I have done nothing. I have just broken down the particular numbers into some kind of an equation. Okay. So if you can see, this 11 is the output for the previous n, right? This 5 is the output for the previous n, correct? And this 2 is the output for the previous n. Similarly, if you have, and before going to the next, let's figure out this also, right? Why you will be seeing the pattern. Here we have taken 1, 1 and 2. The pattern is not consistent, right? In the previous one you can see that, yeah, the pattern is consistent as we are taking the previous output values of n, right? But here how we are getting this, if you can see that, if we do, we just cannot, uh, for this particular scenario, what we were doing, suppose a of n minus 1 value. Okay, so right now we are standing at n equals to 5, n minus 1 means 4, right? So what is the value of a of 4? The value of a of 4 is 11, so we are placing it here. Again, if we are standing at n equals to 4, and what is the value of a of 3? It is 5, right? So we are placing it here. So this is what it's happening. Okay, but what about the plus 2 plus 1 value here? Okay, can we do n minus 1? No, it won't make sense, because when we will come to n equals to 5, we won't be getting 2 here, we will be getting 4. That won't make our answer. So here if you can observe a pattern, this n, this 1, what is the value of, let's check. Okay, what is the value of a of n minus 1? Suppose if n right now is 5, it's 4, right? The value is for this is 11, so we have considered that, but we need the value for that scenario. So let's do by subtracting a of n minus 3. What is the value of a of n minus 3? Since 5 minus 3 gives me 2, so I need the value of 2 here. So when n is equals to 2, the value is 2 here, right? So we have placed that 2 here. This 2 is coming from a of n minus 3. Okay, this 2 is coming from basically here now. Now for this, when a is 4, n is for 4, so when we do, we get 1. So what is the value of a of 1? Here it is 1, right? Therefore this 1 is coming from here. Okay, so I hope you are getting the pattern now. Now you will ask me that, why haven't you checked for n equals to 3? Look, from n equals to 0 to n equals to 3 remains our base case, because if you take a of suppose 3 minus 3, it gives me 0, and a of 0 is 0, right? So till n equals from 0 to 3, it's a base case, but after that the pattern will repeat. How? Let me show you. So when n is equals to 6, what should be the output? According to our understanding, it should be a of n minus 1 plus a of n minus 3, correct? So 2 into 5 plus n is 6, so it will be 3, correct? 2 into a of n minus 1 is 5, right? So what is a of 5? A of 5 is 24, right? Plus a of n minus 4, n minus 3, it is 3. So 6 minus 6 is 3. 6 minus 3 is 3. What is a of 3? A of 3 is 5. Okay, so we'll place 5 here. So it becomes 48 plus 5. I guess it becomes 53 then, right? Yeah, so for n equals to 6 the combinations are 53. To make it sure, you can, if you have time, you can draw the patterns and figure out, yeah, n is equals to 6. So this is the pattern how it goes, right? So a of n minus 1 gives me the previous output of n, okay, and a of n minus 3 gives me the output of the previous third value, okay. So if I'm standing at 5 and I get n minus 3 value, so it is previous to 5 minus 3 gives me 2, so previous 3 value is 2, 2's value is 2, right? So this is the way the pattern comes out, right? So this is our pattern, or this is our solution to the question. Now this shows the solution grows naturally, extends the previous board in two ways, and include contribution from smaller boards for the other shapes, giving a complete count each time. So we are taking the combinations of the previous rather than creating a new one, right? So this is a pattern, because as we go further, when n become, when n is equals to 7, n is equals to 8, we need the solution from the previous boards, right? Because n is 7 is coming after 6, correct? So of course up to 6 we have a combination already stored with us. So why we will calculate newly for n equals to 7? We will try to get it from the previous one, right? So this is where the combination goes. And yeah, coming to the intuition of this problem, seems the problem is a medium level, but yeah, coming to this intuition is a pretty hard thing. But I hope you understood how the pattern goes now, right? So let's move to the next slide. Now how we can simulate this? Very easy. There are the base cases, as I already said, n equals to 1, n equals to 3, n equals to 3. So we will create these base cases and just we will return, if n is equals to any of this number, we will return the output directly. Okay. Otherwise, since the recursion DP come from the recursion, right? So since there are repetitive, there will be repetitive solutions to this because of the recursion. So that we avoid using that repetitive solution, we try to use DP here, so that we can store for, suppose if n is equals to 6, if we don't use DP, the recursion will count this solution again, right? Again it will count. If you remember, I explained the time complexity for this solution will be 2 to the power n. Why 2 to the power n? Because we have, because if you can, if you calculate this, each cell of f of n has two calls, right? Which is n minus 1 and n minus 2, right? N minus 3, sorry. So there are two calls for each f of n, right? So because of that, for each n there will be two combinations called, therefore the time complexity comes out to be 2 to the power n, right? So after that, since this is a DP question and this is a recursive question, but we have to convert it into a DP, because we have to remember the previous n value. To remember the previous 3 value, we have to store it into our DP array, so that when a function is called for particular n, again we have the value stored already, right? So the equation becomes, 2 into function, or you can write solve n minus 1, solve n minus 3, and we store this answer whatever we get into the DP of n. If n is 3, suppose if n of DP of n which is 3, so we calculate the combination for it, okay. And when we call this function, it goes and looks into the DP array again, right? What is the value of n minus 1? So if n minus 1 is here 2, so it will go back and look into the DP array, that what is the value of DP of 2? It is, suppose 2, right? So it will throw it here. Great. And similarly for DP of n minus 3. And since we are asked to divide our complete solution with with modular, so what we do, we divide this complete equation by mod of n, okay, because mod of n ensures answer stays within the modulo of 10 to the power 9 plus 7. Great. So I hope you understood this simulation process also. Let's move to the next slide. What we figured out, a plain recursive solution recalculates the same sub problems repeatedly, exponential time 2 to the power n. Memoization optimizes it by sorting results in an array of T, returning it to top-down dynamic programming. The approach is clean, avoids redundant calculations, and is efficient for large values of n. Okay, so I hope you understood the complete intuition. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. So, in our Python code, we will create an init function or init method, okay, or a constructor, you could say. In that, We will try to initialize the modulo, which will be of 10 to the power 9 plus 7, correct? And we will also initialize the DP array t of minus 1 into 1001, because our n goes from, if I am not wrong, 0 or 1. I guess I didn't remember. Let's check. Okay, our n goes from 1 to 1000, right? So to be in a safe space, we take 1001, right? This is our DP array. We already created it in our init method. Now, when we come into the main function solve, there we will initialize these base cases. If n is equals to 1, if n is 1, what is the output? It's 1, right? Or if n equals to 2, what is the output? It's 2. So that means that we just have to return n, because if n is 1, 1 is the output. If n is 2, 2 is the output. But if n is equals to 3, we have to return 5. Okay. After this, these are the pre-computed tiling counts for small boards with and served as a foundation for larger values. Okay. Now at step 3, after these base cases, since we created a DP array, we have to create a memoization check, which is the most important one, which basically says DP, or here we could say t of n. If it is not equals to minus 1, that means we have already calculated the value for this particular DP. So we'll just return t of n or dp of n, whatever the variable name you keep. Okay. Otherwise, the main compute function, which is dp of n or t of n, whatever you can take, there we will write that there will call the solve function with n minus 1 value, then plus solve function with n minus 3 value, and for this complete we will calculate its modulo. Okay. This recurrence relation builds the current solution using already solved sub problems and ensures we stay within the modulo value. Okay. So after completing all of this recursion and stuff, the main base function, which is num tilings, which is given to us already, there we will just return, or we will call the function solve with the value n. Okay, this will return our answer. So I hope you understood the approach explanation. Let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So here, if you can see, this is the init constructor or init method, whatever you can say. We've initialized the modulo and the dp. I have written here as t. Okay. Then in the solve function, we have the base cases. Okay. And then the dp check, then the main recursion solution, and then we return the self of t of n. Okay. After calculating the value of suppose 3, we have to return its value right back, and in the main function we call the solve function here. Now the time complexity for this complete solution is O of n, and space complexity is O of n. Why space complexity is O of n? Because the value of n is given from 1 to 1000, right? That is why its space complexity is O of n, because we have initialized the DP array with that particular size. And why the time complexity for DP is O of n? Because for each f of k or n is computed only once, right? It is for suppose f of 3 or t of 3, it is calculated only once, right? We are not calculating it twice or thrice. So the value for lookup for this particular thing goes to O of 1, right? Because when value is passed in the function as here, we directly go into the DP and check whether do we have that value or not. So that lookup takes O of 1 time complexity, right? So that is why the time complexity for this particular thing becomes O of n into O of 1. O of n, since we calculated the value for t of 3 suppose, and multiplied by O of 1 to look up the value of for that particular thing. Okay. So I hope you understood the code and time and space complexity. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. For your better understanding, I've already brought down the code here. So here, since we already have n equals to 3, I have taken the example here. So let's do. Okay. So this is the DP array. Now what will happen is that My bad, here in this particular scenario, since we have already taken the base case, n equals to 3, if n is equals to 3, we written 5 here, right? So let's take the example for n equals to 4, okay? Not 3, n equals to 4, yeah. So for 4, we have 11 ways, if you remember. So let's try doing the dry run for this value. So we call the function, we're standing here, n is not equals to 1, neither n equals to 2, neither n equals to 3. We have n is also is equals to minus 1. So if we just do 0, 1, 2, 3, 4, 5, okay. So what will happen now? 2 into n minus 1 will be called. What is n minus 1? N minus 1 is 3. So so the value will be so this function will be called again. We'll check, okay, yeah, we have for n equals to 3, we have 5, right? So this particular, since we have, so we will return 5 directly, correct? Great. Now this function will be called, which n equals to 3. N was 4, 4 minus 1 is 4 minus 3 is 1, right? So we'll go back, we will check, okay, if n is here, n is 1 right now. So when n equals to 1, return n means return 1. So we'll return 1 from here. Great. Now the calculation will be done. 2 into 5 plus 1 gives me 11, right? So for t of n, which is basically 4 here, we will store 11, correct? And we will return it. So the function call is done, right? So this will return 4, this will return 5, 11, okay. And suppose if you had n equals to 5, okay. So what would have happened? N equals to 5. So for 4, it would have been called. We would have checked, okay, so we don't have anything. So this is done. So again, now value for 4 is there, right? Now let me write it here. Function call 1 for 5 is done, in which we passed 4 for the first half. Second half is still remaining, okay. So we came here. Now the function will be called for 4, right? That is a simple recursion understanding. So as we have already calculated the value for 4, what will happen? 3 will be passed here, and for 3 we will get 5. 1 will be passed, and for 1 we will get 1. And the total combination for n equals to 4 will be 11, right? So we will store 11 here. Great. So this will return 11, right? So we'll come back to this function 5, and this will be having 11 with it. Understood? Because this function 4 is called. Now for n equals to n minus 3 will be called, which is basically 2, right? So when we come back here, we see n equals to 2 is there, so return n itself. So 2 will be returned from here directly. Okay. So now the calculation for n equals to 5 will be done, which is 24. So in dp of 5, 24 will be placed, and we will return that particular dp of 5, and the output will be 24 for that. So I hope you understood the recursion, how it's working here. So if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code. And if you are weak in recursion, please go and have the understanding of that. And after that, do a dry run by yourself on 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now since we are familiar with the problem and the solution, let's move to the lead code and code the solution. So let's start by initializing the constructor or the init method. Okay. Here we will initialize self dot m equals to 10 to the power 9 plus 7, and self dot t, which is basically, I will rename it to dp instead, okay, instead of t. So minus 1 into 1001. Okay. Now let's write the main function solve self comma n. Okay. Now if you know that if n is equals to 1 or if n is equals to 2, just return the n, or if n is equals to 3, return 5. This is the base condition. Then we will check that if, okay, I did some mistake here. Okay, if dp of n if not equals to -1, which means that it has been already calculated. So we will just return the dp of n. Okay, and after that, what we do, self dot dp of, let me see one thing. Like, so since we are calling it from a constructor, so we should write self here. Okay, so here also, otherwise it will throw error. Self dot. Okay, so for dp of n, we will calculate 2 into self dot solve with n minus 1. Then we will calculate the mod for this. Okay, we have to calculate the mod for each calls. Fine. Self dot solve n minus 3 mod self dot m. Okay, then finally for the complete function also we should calculate the mod. Fine. Self dot m. Okay, then we will return self dot dp of n. Let's try submitting for the sample test cases first. Okay, so there is an issue here. Okay, I forgot to write the return the function here, self dot solve with the value n. Let's try submitting for the base test cases, sample test cases. Let's finally submit the solution. Okay, it's a typo. Let's try again. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.